The next thing we're going to look at is the process of linearizing data using various functions. If we look at the y versus x data here, y is 6, 12, 24, 48. Well, we can see pretty quickly that the ratio 12 to 6 and 24 to 12 and 48 to 8 is always 2. And since x is changing by the same amount each time, that tells us that this is perfectly exponential data. But that might not always be obvious, and we might not always even think to look at the ratios. Sometimes it wouldn't make much meaning because the x values wouldn't necessarily be equally spaced. What if the data really should have been exponential, but due to some noise in our data taking, by noise we just mean random fluctuations due to interference of various things with whatever it is that we're observing, or random errors in our data taking. If 6 was really was observed to be 5.8, and the 12 was observed as 12.3, the 24 is 23.7, and the 48 is 48.1, then the data wouldn't be perfectly exponential anymore, and this doubling wouldn't just jump out at you. So here we have nearly exponential data with noise. Now we know that our model should be exponential because we don't have all that much noise here. Nothing differs from the perfectly exponential data by more than 0.3. However, well, if we expect the data to be exponential, we're going to linearize it by taking the log of all our y values. And let's see how that works. Now had we used the original data, where y was 6, 12, 24, and 48, the logs would have been 0.78, 1.08, 1.38, and 1.68, which is perfectly linear. The difference between any two of these is exactly 0.3. Now that's not really true that it's exactly 0.3 because there's some round off in here, but it turns out that the round off has been unusually cooperative, and we don't notice any differences down to the 3 significant figures that we've used here. So that when we linearize perfectly exponential data, we get perfectly linear log y versus x data. Now, of course, our data is not perfectly linear. Instead of the 6, we have the 5.8. Instead of the 12, the 12.3, and so forth. So when we take the logs of these data points, we get this nearly linear data. Okay, this is nearly linear. 0.76 to 1.09 is a difference of 0.33. Then we have a difference of 0.28 and a difference of 0.31. So that's not perfectly linear, but they're not changing by much. That's close enough to linear that we're going to be able to get a very good linear model. And this is what we do next. Once we've linearized the data, well, the reason we linearize it is so that we can fit a linear model to it. So we sketch a graph of the function, and we can get our linear model in any one of several ways. One way is to go to derive and put our 3 data points into derive, 1.76, 2, 1.09, and so forth. Okay, that's going to be the most accurate way. If we do a linear fit to that, it's going to give us the the very best possible linear function fit to this data. However, all we do here is we sketch a graph and then we make an estimate. Okay? Now, I actually made this estimate. I cheated a little bit by doing some extrapolation, but I certainly didn't use derive. Anything but just what I could see in the graph. If you drew a very accurate graph, you might well come out with a model very close to the one that I've come out with here. I estimated that the y-intercept would be about 0.48 and the slope would be about 0.305. Now this is a graph of log y versus x, so we say that the log y is 0.305x plus 0.48. Then we solve this for y to get a model for y, because that's really what we're after. We want y as a function of x. And the solution is not overly difficult. We have log y is 0.305x plus 0.48. Well, that means that y is 10 to the 0.305x plus 48. Now 10 to the 0.305x is 10 to the 0.305 raised to the x. You've seen that sort of thing a lot. And 10 to the 0.48 is just 10 to the 0.48, which is about 3.02. 10 to the 0.305 is 2.02, 10 to the 0.48 is 0.302, so our model ends up being y equals 2.02 to the x times 3.02. We write that model here, y equals 3.02 times 2.02 to the x, and then we bring that model on up here and we make a column for that model. Okay, using the x values 1, 2, 3, and 4, which is what we started with, we evaluate 3.02 times 2.02 to the x, and we get 5.8, we get 6.1, 12.2, and so forth, which agrees very well with our original data, 5.8, 12.3, 23.7, and so forth. And also note that each of these points is closer to the original y value. 6.1 is closer to the original hypothesized y value 6 than 5.8. 12.2 is closer than the 12.3. And I believe the other two will probably come out closer to the original values that we started with than these. Maybe not the 48.1 because that's already pretty close. You should validate that and verify it for yourself.